So, today I will demonstrate Fresnel's zone plate experiment, or we tell zone plate experiment. So, I will show you this is a zone plate, this is a zone plate. You can see this, that surrounding are black, and inside this black there is a transmitted part, transparent part. Okay, in that transparent part you can see this at the center it looks black. So, and then this transparent that part are divided into many concentric circles, okay. The area of each circle is basically called zone, Fresnel's half period zone. So, there are many concentric circles which are Fresnel's half period zones. Now, if we just stop, we just make that off the alternate zones, means alternate zones will be blocked and other alternate zones will be transparent. So, if so, then that we tell that it is a zone plate, Fresnel's zone plate. And now we will use the zone plate for experiment. So, this zone plate is basically it behave like a lens, convex lens. Now, convex lens have only one focal length, but this zone plate have multifocal length. Okay. So, what are the focal length of zone plate? That we want to measure. Also, we can find out what is the radius, of these concentric circle. So, we will perform the experiment to find out basically the radius of the Fresnel's zones. Okay. So this very in computer you can make this dark by this kind of actually Fresnel's zone, this kind of you can make dark bright alternate. These circles will be black or blocked, and alternate circuits, next alternate circles will be transparent. Okay. So, what will be the radius of circle? Actually, that it should be the square root of m. What is square root of m, that I will discuss. So, basically we get if you can construct this type of concentric circles with black circles and white circles. Okay. And if you take print on this type of transparent sheet, okay. So, then that was a one pieces we have cut from here, and that we are using basically as that piece we are using for our experiment. So, it's a very easy to construct this zone plate, and this plate we will use for our experiment purpose. So, to understand that experiment, actually we have to understand the theory behind this experiment, that is very important. So, here as I told this zone plate will behave like a convex lens, but it has multi-focus convex lens. So, the relation we will get, I will show you how it has come. So, relation we will get like this, 1 by A plus 1 by B, and this Sm square is the basically Sm is the diameter of the mth zone, mth Fresnel zone, okay, and this m is the order of the zone, and lambda is the wavelength of the light whatever we will use for that experiment. So, what is A and B? A is basically the source distance, light source distance from the zone plate, and B is the screen distance from the zone plate. So, as if the CPT is the lens, so this the A is the object distance and B is the image distance. So, you can see, so like just 1 by the U and V. So, A and B if you equate to the U and V, so it is like 1 by U plus 1 by V equal to 1 by F equal to 1 by F. So, 1 by F basically here m lambda by Sm square. Sm is the radius of the mth zone, mth zone of the zone plate. So, this one, so here you can see this focal length basically for a particular lambda, it will focal length of this zone plate will depend on the wavelength of the light. It will depend on the, because your if you convex lens you take, it does not depend on the wavelength, focal length does not, it is fixed, and here basically you can vary the focal length and easily you can construct this type of band which you can use as a like a convex lens, you know. So, lambda the wavelength and radius of this basically, if you see here, yes. So, this radius of the zone, if you know the relation, some relation of the radius of the zone with the this zone number, m is 1, 2, 3, 4, 5 zone number. So, there is a relation I will discuss. So, this relation is basically this Sm is equal to square root of m. So, square root that m is 1 to integer value 1, 2, 3, 4. Okay. So, basically S1 is 1, S2 is square root of 2 means 1.414, then S3 is square root of 3. So, m will be 1.732. Okay. So, so theory has given us the what will be the radius of the zone plate, radius of the half period zones of the zone plate. Okay. And whatever I have showed you. So, using this formula basically one can, in computer one can construct this type of zones, and then we can take then in computer itself we can make alternate one dark, and you can take print on the sheet, and then it's you can use as a zone plate. Okay. So, experimentally we can find out what is the focal length of this zone plate, as well as what is the radius of the zones of different number. Okay. So, that you can find out from the experiment, that is what we will demonstrate. So, how this formula has come, so in details I will discuss before demonstrating the experiment. So, you know this zone plate that is I think so this whatever the it is working like a like a convex lens. Okay. So, that this is basically diffraction phenomena. It is because of diffraction. So, this type of diffraction, there are two types of diffraction. One is Fresnel diffraction, another is Fraunhofer diffraction. So, this distinction between the Fresnels and Fraunhofer is basically depending on the distance of the object and the screen from the grating, or from the yes. So, in case of Fresnel diffraction, the object and the screen, okay, so that distance are either both or one of them will be at finite distance. Okay. If both are at infinite distance, then we tell this the Fraunhofer diffraction. If one of them or both are at finite distance, then we tell is the then we will see the diffraction that is called the Fresnel diffraction. Okay. So, diffraction effects obtained when either the source of light or the observing screen or both are at finite distance from the diffracting aperture or obstacle, okay, come under the classification of Fresnel diffraction. So, whatever the experiment on zone plate will demonstrate, that is basically Fresnel type of Fresnel diffraction type. Okay. So, here, so Huygens principle, you know that if we have a source, now this you will have the wavelets. Okay. So, if this we tell the primary waves or primary wavelets. Okay. So, then if you have a here hole aperture, okay, its dimension is very small compared to the comparable to the wavelength, then only you will be able to see that this diffraction phenomena. If this whole this aperture is very big compared to wavelength, so you will not see the diffraction phenomena. So, now this it is a aperture, it can be one obstacle also of small size. Okay. So, now this wavefront will fall on it, and now this on this wavefront each point will act as a new source, and it will generate waves. So, that we tell wavelets. So, we call them secondary wavelets. So, these secondary wavelets will generate okay, from different points, and they will interfere. So, actually interference among the secondary wavelets or the diffraction. Okay. So, here it's a small pinhole source, and from there it is falling on a screen having a small aperture. Okay. So, now this Mn portion wavefront will be allowed to pass through it, and then secondary wavelets will be emitted in all directions from here. Okay. And they will interfere, and on this screen you will get the diffraction pattern. Okay. So, here wave can move in all directions, wave can move in all directions. So, it can go backside also, but experimentally no reverse wave traveling back towards the source is found. Okay. So, that is why this in the theory, so obliquity factor is considered. So, that is k theta obliquity factor equal to half 1 plus cos theta. So, that means it is going in forward, its theta is 0, this theta is 0. So, cos theta is 1. So, its factor is 1 plus 1 into half. Okay. Now, this if theta is 180 degree, then cos theta is minus 1. So, this obliquity factor is 0. Okay. So, this obliquity factor will be multiplied. So, that will basically restrict the or it will represent this experimental fact that reverse wave travelling back forward to the source will not be there. Okay. So, that is called obliquity factor. Now, so that diffraction, Fresnel type of diffraction generally you can see by a circular aperture. Okay. So, these are circular aperture and this light are coming, it may be parallel light are coming. So, plane wave front. Okay. So, source is at infinite distance, screen is at finite distance. So, then you will get diffraction pattern on this screen like this. Okay. Concentric circle kind of diffraction pattern you will see. Okay. So, if it is hole, circular hole, so you will get circular pattern, bright dark patterns you will get. Okay. So, here depending on the I think it depends on the distance. So, this center can be bright or can be dark. Okay. And also you can see this type of diffraction pattern for a say circular obstacle, this kind of things. Okay. If you take a disc, so light is falling, so no light will pass directly through this disc, but light will go from the surrounding. Okay. So, if this is a very small object, small disc, so then you will see the diffraction pattern, and on the screen you will see this type of again pattern of the diffraction. So, bright dark circular pattern you will see on the skin. Okay. So, surprisingly you will see that the center circle will be always bright, So, so this is obstacle. So, no light passing through this in this direction, So, but at this center, so light is obstacle, but still you are getting that the center circle is bright, always this is bright. Okay. So, so that is because of the diffraction and Fresnel type diffraction, of course. So, so zone plate is basically of this kind. Okay. So, these transparent region are divided. So, wavefront will pass through this circular aperture. Now, this circular aperture on this wavefront will be of this shape. Now, this wavefront, if we can, so how this pattern are observed, are formed. To understand that one, so that Fresnel's half period zone, that concept is introduced by Fresnel itself. Okay. So, that I will discuss now, how that Fresnel's half period zones are considered for explaining this type of diffraction pattern. Okay. So, So these Fresnel's half period zones, okay. So that wavefront, you have a wavefront, and this is the point on the screen, okay. So light, basically this from wavefront, secondary wavelets will pass in all directions. Now if I consider this point, now from different points of the wavefront, okay, so wavelets, secondary wavelets will come at point P. That means light are coming from different distance at point P. Now as I told, the interference among them will produce the pattern, okay. So superposition of the secondary wavelets at this point will give me the intensity of the resultant intensity at point P, right. So amplitude, so here you know this, the two light are coming, they are in opposite phase, obviously they will cancel each other, you will not find any resultant intensity, resultant light here, okay. If they come in phase, so that will be that will increase the intensity of light. If they come in opposite phase, they will destroy each other, right. So if I can calculate the light coming here, what are the phase relation among them, then I will be able to calculate the intensity or resultant amplitude of light at this point, and corresponding intensity I will be able to calculate. So that's what Fresnel's, that he suggested a very beautiful way to do that. So what he has done, so from P, this wavefront or the aperture or the circular aperture, okay, center of the circular aperture, if through which this wavefront will pass through, okay. So if this distance is B, now you take, so light is coming from this center, so that is the, when it will reach here, so this distance is B. No, now light will come from this point. If this distance is B plus lambda by 2, then you can tell the path difference between these two light coming here, it will be lambda by 2. That means the phase difference will be pi. So they will be in opposite phase. So if we take distance from P on this aperture, okay, by taking that distance lambda B plus lambda by 2, B plus 2 into lambda by 2, B plus 3 into lambda by 2. So consecutive that separation of the distance or difference of the distance will be lambda by 2, half wavelength. So taking this distance, if you draw here, okay, if you draw the circle, concentric circle here in such a way that the distance from this circle point on this circle to this point on the screen P, if that is B plus lambda by 2, then next one on the next circle, this is B plus lambda, etc. So we can show that light will come from the alternate zones, will be in phase. Alternate zones will be, so these are called the zones, and it is called half period zone, Fresnel's half period zone, because the light coming from from the consecutive plane. So, their path difference will be lambda by 2 or phase difference will be pi. Okay. So, now from the center, if you consider this one, okay, it can be spherical, wavefront, it can be planar wavefront also. So, from center here, center of the aperture O. So, now the radius of the circle, concentric circle are SM, M is 1, 2, 3, 4. So, S1, S2, S3, and their corresponding that distance, that screen, that is as I told, B plus lambda by 2, B plus lambda, etc. So, if so, then this basically, this is the source. From here, this aperture, circular aperture is there. Okay, screen is there having the circular aperture. So, light will pass through this wavefront, will pass through the aperture. So, on the aperture, if you consider this wavefront, now that wavefront you are dividing into concentric circle, and these concentric circles are constructed in such a way that this path difference between the consecutive circle, light coming from the consecutive circle reaching at point P, this path difference will be lambda by 2 or phase difference will be pi. So, that is the Fresnel's half period zone. Okay. So, that's what I explained you, what is S, what is B, what is lambda. So, then then what I can do, I want to find out the area of each Fresnel's zone plate. Okay. Each area of Fresnel zone, not zone plate, zone. Okay. So, this is the source, and this is the screen, and this is your this is the circular aperture, means circular wavefront. Okay, wavefront in circular shape. Okay. Now, here you can see, if it is at finite distance, source is at finite distance, so obviously you will get the spherical wavefront. Okay. So, wavefront here, okay, here. So, this distance, if it is A, so this will be also A, this will be also A. So, they will be in same phase. Okay. But if you take a normal from Q on this HP, okay, on this line. So, that Q dash is the footprint on this line. So, here you can see that this, when light is reaching here, and basically you can so this distance A, when light is reaching here, the same time light will reach here, and from there when light is reaching here, okay, that is B, and light also from here it will reach at this distance, so that is B. So, total length of the light here you can see this to reach to the screen. So, that is A plus B. Here why we have drawn the circle, spherical wavefront, basically because they are in finite distance. If it is infinite distance, then we could write a planar one. Okay. So, now light is passing following this path. So, this will be A plus B, and light is going following this path. So, this one is A and this one red circle, you can see this one is B. So, A plus B and additional path QR, it has to traverse. Okay. So, light is coming like this and light is going in this direction, in this way. So, path difference or length difference will be between these two rays light will be here, definitely it is QR. Okay. So, that QR one can find out. So, here I have shown you. So, this is the rectangular triangle. So, you know, just I will not just discuss. So, you can find out easily. Okay. So, this is the standard. So, from here this is the center, this is the O R dash and O Q dash, that is basically equal to QR. So, that is nothing but the path difference delta. So, delta here equal to O Q dash plus O R dash, O Q dash plus O R dash, and from the right angle triangle, okay, you can find out that O Q dash equal to A square by 2A and O R dash equal to A square by 2B. So, basically del you are getting here A plus B by 2AB A square. What is S? S is the you can see this is the basically is the diameter of the circle, is the diameter of the here wavefront. On wavefront basically you have concentric circle, that center of the circle is O, okay, and from here, so you have concentric circle. So, the radius of the concentric circle will be S, okay, and source distance from this center of the circle is basically A, and skin distance is basically B, okay. So, whatever here you are getting this path difference, it will depend on the source and skin distance, as well as it will depend on the radius of the concentric circle, which we are telling Fresnel's half period zone. So, for mth Fresnel zone, SM is the radius and path difference is SM square. Okay. Now, path difference when it is m lambda by 2, means you will. So, when this path difference will be m lambda by 2, then what will happen? These two light having the path difference lambda by 2 when m equal to 1, then lambda by 2. So, they will be in opposite phase. Lambda by 2, that corresponding phase will be pi, opposite phase. So, you will get dark, and when lambda is 2, okay, lambda is 2, then it is lambda, then you will get bright, okay. So, you will get basically the region, you will get on the screen, you will get region of dark bright, okay, and you will get basically in circular form, because your object is of circular form. So, basically diffraction, whatever we see, either from reflection or refraction or diffraction or interference, that we basically see the image of the object, okay, since our object is of circular form. So, on the screen you will see the image, and that image we are getting because of the diffraction, in this case diffraction. Okay. So we will see the circle, concentric circle, and that concentric circle whatever we will see here, first order, second order, third order, fourth order will get. So alternate order will be the dark and next alternate order will be the bright. So basically as I showed you, I think you will see basically this type of, on the screen you will see basically this type of pattern, diffraction pattern. Okay. So area, so I got the radius of this is concentric circle, right? So what I got? I think I can I calculated and I got it. Let me see where I kept. Yes. That I got. Here. So I got basically here. I got this basically. This is the radius of the circle of different order, right? So here you can see this S m square equal to m lambda by 2 divided by this part. Okay. So now if you know the radius, so you can find out the area. Now the area of each zone, so area of each zone or any zone, so you can write pi r square, here s square, sm square minus pi s m minus 1 square. Okay. mth and m minus 1, that the two concentric one. Okay. So difference of the between these two area will give the area of the between these two area between these two circle. So that you can calculate. So that will be SM, capital SM. So area of the mth zone. So that will come A by A plus B pi B lambda. So interesting fact is that this area is independent of M. Okay. So that means you can say that area of each zone, first order, first zone, second zone, third zone, area are same. Okay. It is independent of M. So area are same. So this Fresnel zones, about the Fresnel zones, what we came to know, what you know now, that area of each zone is same. Okay. And light will come from each zone to the screen at a point P. So this so alternate light from alternate zone will be in phase. Okay. But light from the two consecutive zone, so that will be out of phase. Okay. So now if we can block the alternate zones, okay, means say 1, 3, 5, 7, so odd zones, if we block it, okay, make it black, and even zones 2, 4, 6, if you keep it transparent, then from that, instead of circular aperture, if you use this one, okay, So whole region is not transparent. So zone wise alternate one are transparent and other alternate one are obstacle block. So then light will come from this zone through this zone plate and this to the skin. Then what we will see, what will happen? Okay, so that's the basically we are going to study. We are going to study. So what will happen if we use this type of zone that is called zone plate, Fresnel's zone plate. Okay, so what will happen about the amplitude reach to the skin at a point P. So amplitude at P due to whole wavefront. So amplitude, so from region 1, because amplitude from each region, although area are same, but due to obliquity factor, the amplitude will not be same. So amplitude here, the total light coming from a zone, So that's the so from first zone it is amplitude A1, second zone A2, A3, A4, etc., etc. Okay, and already you know that they will be alternate one will be in phase and the even one will be in phase, and odd one will be out of phase. Okay, with respect to the even one or vice versa. Okay, so we can resultant amplitude we can add this total amplitude of add this all individual amplitude A1. So next, if it is plus A1, if we consider, then next will be minus A2, okay, because they are in opposite phase. So then plus A3, minus A4, plus A5, etc. Okay, up to M. So if M is odd and M is even, so here I will not just describe, it will take time. So here you can show, if it is odd, you see, I can write A1 is A1 by 2, A2 is A1 by 2 plus A1 by 2, A2, A3, A3 by 2, A3 by 2, okay. So this I put in a bracket. So as if average of A1 and A3 will be equal to the A2, okay. So that way this will be cancelled, only this and this term will be there, A1 by M, A1 by 2 plus AM by 2. Even for M is, when M is even, this is M is for odd, so then you will get, same way if you proceed, you will get A equal to A1 by 2 minus AM by 2. Now due to obliquity factors, I explained it, okay. So mth zone, okay, it's a outer, so obliquity this factor, so theta will be higher. So this term will be this k theta about this obliquity factor, it will be smaller. So AM by 2 will be very, very small compared to A by A1 by 2. So one can neglect this AM, so it will be A by 2. Okay. So if all zones are open, then the amplitude, resultant amplitude will get at point P, that is half of the amplitude of the first, whatever the amplitude in first zone. She is very small one, small intensity. So it will be A1's intensity square of the amplitude. So it will be A1 square by 4. Okay. So that will be the amplitude. Now if I block alternate one, then what we will get? What we will get? It's obvious. A will be A1 plus A3 plus A5 plus A7, etc. Or it can be A will be A2 plus A4 plus, so all will be added, all will be added. Okay, so when all are when all are open, transparent, circular aperture is transparent, you are getting only A1 by 2. Whereas if alternate one are blocked, you are getting, it's a just half, amplitude is half of one zone, and on the other hand you are getting summation of amplitude of all alternate zones. So you can imagine A1 plus A3 plus A5 plus if it is say M is 1000 or 100. So now intensity is square of that one is 10,000 or I don't know, 1000 square is 10,000 times more than the intensity of when the whole region are open, transparent, then whatever the intensity will get, if alternate one is blocked, you will get, for M equal to 100, you will get 10,000 times intensity more. So it's you can think that we focused as if this using this zone plate, one can focus the light at a point P. Okay, so it is nothing but like a convex lens. We use convex lens to focus the light at a point, at the focal point. Sometimes one can burn the papers also. Okay, so this is the beauty of this zone plate. Okay, so now I think I have anything else to tell you. Yes, so I think so we'll, for doing experiment, what is the working formula I will use, that is okay. So if I just summarize it, so we have seen the area of each zone is approximately same. So that is area SM, capital S, small s we have considered for, small s we have considered for the radius of the zone. So that is AB by A plus V pi lambda. So B I have just taken here, and A is the object to source distance and B is the object to screen distance. Okay, and when all zones are open, then amplitude will be half of the amplitude of first zone only. If alternate zones are exposed only, then it will be, amplitude will be A1 plus A3, A plus A5 or A2 plus A4 plus A6, etc. Okay. So that's what from the discussion we learned, and then what we are getting, and you have seen that A plus B by AB by 2AB into SM square equal to M lambda by 2. That's what we have seen, right, when we derive. Again, should I show? Yes, I think here that's what that relation we got it. Okay. So this relation is basically we will use for this experiment. So now you have this relation in your hand, where SM is the radius of the mth Fresnel zone, and this is basically the path difference between light from mth zone and first zone. Okay, the path difference of light from the mth zone compared to the first zone. Okay, so this is the relation we got. So for a given A, B and lambda, means if you keep constant the source distance, the screen distance, and the for a particular light wavelength is constant, then the zone must have radius Sm equal to square root of m. From here you can easily see Sm square equal to m, because lambda, a, b are constant. Okay. So, from here you can tell that Sm means the radius of the zone must be square root of m. If zone plate with concentric circles of radius square root of m, so now it is in your hand how to construct that also I showed you, discuss you, are preferred, and only odd or only even zones are blocked, then it works like a lens. Then it works like a lens, because 1 by A plus 1 by B equal to m lambda by Sm square, okay, radius square. Okay. So, this equal to, you can think this 1 by F. So, this is the source and screen distance. So, it is just like a source u and screen distance v, image distance. So, equal to 1 by F. So, this relation is for convex lens. So, from here you are getting this the relation. It is a similar relation like convex lens you are getting, where important is this part, okay, 1 by V plus 1 by U equal to 1 by F, where 1 by F is m lambda by Sm square. Okay. So, here you can see for a particular wavelength. So, now F focal length will depend on order on m. Okay. So, for different m you will get different focal length. Okay. So, it is not one focal length, you know, it is not one focal length. Okay. So, it is the m number of focal length you will get for a particular zone plate. Okay. So, that's why we tell this the multifoci convex lens. Okay. So, this relation is in your hand. Now, what we want to do here, from here you can see, if I can find out the focal length, okay. So, for experiment what we will do, from this relation you see that if, so A is the source distance, if now source, if I take parallel rays, okay, source, that light is falling on the zone plate, if it is parallel, okay. So, then we can take this A is infinity. Okay. So, object distance is at infinity, right. So, 1 by A it will be 0. So, we will design the experiment in such a way, so this part we can make it 0. So, now 1 by B is nothing but the distance of the screen, okay. So, this 1 by B will be equal to 1 by F, okay. So, F will be basically B, okay. So, experimentally if we can find out the object distance, right. We have to find out the image distance from the zone plate, okay. Object distance is at infinity. If we can find out the image distance from the zone plate, then we know, so that is basically nothing but the focal length. Now, as I told this, it will be multifoci. So for m equal to 1 we will get f1 or b1, right. So f2 will get for m equal to 2, okay. So basically we will get for different order. So so what we have to do? We have to find out the position of the we have to find out the so if light focus, okay, if light is focused, so it will be focused at different distance. So if we can find out this different distance, so that will be basically f, and so that will be different f, f1, f2, f3, and that will be for m equal to 1, 2, 3, etc. So basically we will find out the b or f, bm or fm for different f, for different m. Now we will plot say 1 by m and f is b, okay. If we plot, so we will get a straight line, that is the slope. So that slope will be lambda by sm square, okay. So 1m versus 1m, and then equal to m okay, m sm square f, okay. So this will be the slope, okay, this will be the slope. And so basically, so we'll experimentally find the data and we plot this graph, and from graph we will find out the slope. And if you find out the slope, then you can able to find out the sm, okay. So sm you will get, so for s1, s2, s3, etc. you will get, okay. And then experimentally that radius you are finding out. So then you compare with this relation, sm should be square root of m. So this is the theoretical value. Now experimentally you can find out and compare it, whether it is following this relation or not. So that is the experiment will demonstrate, okay. So I think I will stop here now, and this in next class I will just demonstrate this experiment.